before the break, we talked about how that PO2 is the #1 influence of hemoglobin saturation. In fact, it gives us that sigmoid-shaped curve. Other things determine saturation, like temperature, blood pH, the partial pressure of CO2, as well as this enzyme called BPG, which I'll describe later. But for now, let's go through those things. Other influences include, let's say, an increase in temperature. That causes more oxygen unloading. When the blood becomes more acidic, that causes more oxygen unloading. For example, when you accumulate CO2 in the blood, that causes more oxygen unloading. Also, when you accumulate an enzyme called BPG, all of these things, put a bracket around it, facilitate, you increase oxygen unloading. All of these things occur when you exercise. So during exercise, you get increased body temp. You get a lactic acid buildup in the muscle. You get more CO2 accumulating in the tissues. You have an increase in BPG. Exercise, put a star next to it. Put it in chemistry form. Oxyhemoglobin. The reactant, the products are hemoglobin not saturated, O2 is free to leave the tissues and give oxygen to the working muscles. And the equation can go both ways. But what I'm saying is exercise increases the unloading, so it tends to push the equation to the right. Okay, so there's more unloading than loading. All right, that's one thing I wanted to know. So these other four things after PO2, they don't determine the shape of the curve, but they basically make it easier for oxygen to unload. Okay, well, here's an example of when I talked about the plateau being good for external respiration up here. They show man at sea level. He's at the beach, where PO2 is about 100. Saturation is nearly 100. It's 98%. They show someone in the mountains at altitude, where hemoglobin saturation is 95%. The PO2 has dropped to about 80. Not a huge drop off. So the plateau is good for external respiration. Here they show the internal tissues. In resting tissues at a PO2 of 40, right there, saturation is at about 75%. She's just resting reclining at the park. Okay, this person is metabolically active. He's swimming, right? And they say PO2 of about 20. Here's PO2 20 right there. You get a much more drop off. You're about 40%, 35% saturated. So he's exercising. So what I was saying is you get more O2 unloading. In fact, what you actually do when you increase your exercise activity enough is you actually take the whole curve and you shift it to the right. You shift it down and to the right, what I drew in red. It shifted down over here, but for most of the curve, it shifted to the right. This is the effect of exercise. You facilitate more O2 unloading. You shift the curve to the right. And that's a very important concept I want you to know. It's kind of like, I use a chair analogy. Under normal conditions, say you're at rest. It's like you're sitting in a regular flat chair. It's as easy to get in the chair as it is to get out of the chair. But what I'm saying is when you exercise and you change this metabolic profile, you take the whole curve and you shift it. That means you're better at unloading O2. So it's like if you took the chair and you shift the whole curve down and to the right, the chair is more slanted. It's easy for you to slide off the chair because it's slanted like that. You can still load, it's just easier to slide off. That's kind of like what you're doing with this red curve here. You're facilitating more unloading. Why? Because you're exercising, because you need to deliver more O2 to the tissues, and that's what I say here. More O2 diffuses down a larger partial pressure gradient. You're providing more oxygen for the working muscles. More O2 delivered to working muscles. So during the condition of exercise, just start to check it off. This curve shifted down and to the right is because of these changes there. Increased body temp, decreased pH, increased CO2, increased BPG. All right, so to wrap it all up, this right here, these four things, increase the oxygen unloading. Of course, there's a term for it. This is called the Bohr effect. B-O-H-R, it's a person, it's a physiologist. The Bohr effect is during exercise, these changes, you facilitate the oxygen unloading. Cause a rightward shift in oxygen hemoglobin saturation curve. The chair is slanted down, easier to slide off. I have one slide on BPG because I haven't mentioned that before. BPG is an acronym for 2,3-biphosphoglycerate. It's a, well, let me describe what it is. RBCs, erythrocytes, are specialized for non-oxidative metabolism. They don't metabolize the oxygen they transport. Okay. So one non-oxidative enzyme is 2,3-BPG. Let's remember that erythrocytes, they also don't have mitochondria or the nucleus, so they need this non-oxidative metabolism. BPG is one of those things that helps them do that. However, BPG binds the hemoglobin at a site that negatively affects the binding of O2 to HB. It kind of like it bumps it off. BPG levels are elevated during exercise. So BPG during exercise is bumping off the O2 so you can deliver it to the tissues better during the workout. Here's a couple of pictures showing you the normal curve as a solid line, and you shift the curve one way or to the other due to the dotted line. Okay, so I already told you how these four things shifted to the right, down and to the right. You could shift it the other way. you can predict if, for example, an increase in body temp shifts it to the right, a decrease in body temperature shifts it to the left. If it's more acidic, to shift it to the right, more basic, shifts it to the left. So if you just reverse all the arrows, you shift the curve the other way, up and to the left. What you're doing is, you're saying you favor loading, not unloading. You can unload, it's just harder. At any given partial pressure of oxygen, hemoglobin is more saturated. It's like if you took the chair and made it slant up instead of down. Once you get your behind in there, it's harder to get out. You can, it's just harder. So I got a lot of stuff on the board. Is there any questions before I proceed about hemoglobin saturation? I got a lot of things there. The number one that's the most important is PO2. But these other 1, 2, 3, 4 things influence the curve. You shift it one way or the other. If you exercise, shift it to the right. For example, if you reverse it at all, you shift it to the left. The shifting of this curve down and to the right during exercise, okay, is the Bohr effect. It facilitates the unloading of oxygen from hemoglobin of blood passing through active muscle beds. So your blood is different during exercise as opposed to now during rest. That's why for our lab, I want you to do some exercise so you can kind of see some differences. I'll get to that. This unloading of O2 makes it available to tissues to support the increased metabolic demand. You're working out, right? Let's shift gears. Now I want to talk about the transport of CO2. And before the break, I gave you all the numbers. I said 100% is like 60 ml CO2 per deciliter, and I broke it down for you. Remember that? 7% was dissolved. I was like 5, 23% was bound to hemoglobin, called it carbaminohemoglobin, right? It was like the 15 mils. And the rest of it, about 40 mils, is in the form of bicarbonate, HCO3 full negative charge. Okay, so this is kind of a picture of it, either dissolved or bound to hemoglobin or in the form of bicarb. Extraction of CO2 from the tissues. Think of CO2 as a waste product building up in your tissues. You gotta get rid of it. Through the active ventilation, the partial pressure of metabolic waste CO2 is kept low in the alveoli. This creates a gradient for CO2 to move out of the tissue into your blood to the alveolar spaces in your lung, and you breathe it off to the atmosphere. Here's a picture of that. So you're at rest or you're at exercise. CO2 is constantly accumulating. Blood is flowing by. You have to get it from the tissues to the blood to get it to your lungs so you can breathe it off. As long as you keep breathing, you'll keep the alveolar air at 40. So there's this slight gradient, the 45 to 40, which is basically sucking the CO2 out of your tissues, as long as you keep breathing. So it's low in the lungs, you get it out of your tissues that way. Now the biochemistry I want you to know is shown here. Let's look at this equation. Erase this. So metabolic CO2 in the form of carbonic acid, it can then dissociate to give a proton, a hydrogen ion. Because ventilation affects CO2 level, and because CO2 affects the hydrogen ion concentration or pH, ventilation affects your blood acid-base balance. So the equation on the bottom is, you're basically hydrating CO2. So here's water. So let's put CO2 in front of it. If you combine those, it's kind of a slow reaction because those are kind of inert molecules. You need an enzyme to speed it up. That's carbonic anhydrase, right over here. Carbonic anhydrase, an enzyme that will speed up the chemical reaction of of CO2 and water to give you H2CO3 is carbonic acid. It's a weak acid that partially dissociates, giving up a hydrogen ion. There's a full negative charge, and you acidify the blood. Okay, so this is carbonic acid, not to be confused with bicarbonate. And that's the hydrogen ion that can acidify the blood. So that's why CO2 affects blood chemistry, the acidity of the blood. So carbonic anhydrase is the enzyme that quote unquote wets the CO2. And it's actually not in the plasma, it's on the surface of the RBC. So in this picture, imagine your muscle cells building up CO2, and you have to push the CO2 into the plasma compartment of your blood. You can either just bubble it in, like soda pop, and just have some of it dissolve. It'll be in the plasma compartment. Another way is you combine it with hemoglobin. Okay, now here's the thing. Blood is flowing by, and normally is 98% saturated. Okay. Make a connection here. I'm going to go back to the curve slide so what I said will make sense. Blood is going to come, but it's coming fully oxygenated. At PO2 100, and you breathe here, it's 98% saturated. So that's the blood you're circulating to the tissues. Hemoglobin is full. It has no room to bind CO2. I don't know, let me give a simple analogy. Like, you ever well, it's happened to me, right? I used to take the bus to school when I was in grad school, and I looked down the street, and the bus is coming. And I can see that the bus is completely full. So am I able to get on the bus? No. But what happens if the bus stops and people get off? I can get on then, right? Yeah, because then they made room available. It's kind of like that with blood. Blood is coming in fully oxygenated. There's no room on the bus because it's full of oxygen. But CO2 is standing at the bus stop waiting to get on. But it can't get on unless oxygen gets off. Okay? So what's the PO2 at your tissues in rest? What's the number? 40. What's the saturation at 40? 75. So some gets off, 75%. So it's like almost 25% can get on, right? 25% of CO2 can load, but what must first happen, O2 must vacate a seat. Okay, let's go back to where I was. All right, so here we go. It's like, boom, I want to get on the bus, but O2 has to get off. Okay. It's already full, but once one of those O2s gets off, it's like, I can get on. So here's like, in a blood vessel, I got all my O2s are on there. I got my CO2s. They're standing at the bus stop. They want to get on the bus, but they really can't. Okay, at least in terms of hemoglobin. So once it goes by, O2 gets off, CO2 gets in the blood, bound to hemoglobin. Okay, so that one got on. Okay, it turns out, as a whole, 23% is bound hemoglobin. We call it carbaminohemoglobin. It's already in your nose. The majority of blood is doing this chloride shift where, well, I'll tell you about that later. Okay, basically this equation here. Okay, on the surface of the RBC, you have carbonic anhydrase. So I have this reaction happening twice. Slowly in the plasma. Why slow? There's no enzyme. Fast on the surface of the RBC. Why? I put Ca there, it's hard to see. The enzyme is there. So most of the CO2 is in the form of bicarb. Let me show you a picture of that. It's a professional picture. Let me turn the lights off. This is gas exchange at the peripheral tissue. It's internal respiration. And I have Bohr and Haldane on there. Bohr was oxygen unloading when you're exercising. So let's assume this person is exercising. Do you unload more or less? More. Very good. The Moores have it. That's right there. Okay. And in fact, this reminds me, there's a standard that's kind of taught in terms of oxygen unloading. It's called P50, and I want you to know it. So let me P50 is oxygen tension that provides 50% hemoglobin saturation. So we're talking about Bohr-Haldane here. Let me go back to the normal curve once again. Sorry to jump around, but I keep talking about it, so I might as well get it back on the screen there. So I'd say I gave you a this is like a med school standard, right? P50, the oxygen tension, that's PO2, right? Tension is pressure. The PO2 that provides 50% saturation. Now, what is 50% saturation? They don't have it, kind of annoys me. It's somewhere here, between 20 and 30. It's 27. 27 millimeters of mercury usually gives you your P50. Under normal conditions, P50 is 27. If you kind of eyeball the graph, go to 27 on the x-axis. Here's 20, here's 30, 27, it's about 50. Gives you 50% saturation. Okay, that's under normal conditions. Let's say you do the whole thing where you shift it one way or the other. Talking about the Bohr effect. With the Bohr effect, did you shift it to the right or to the left? You shifted to the right, that is correct. So, okay, if you shift the curve to the right, does P50 increase or decrease from 27? you increase it, okay? So in your mind, if you're very visual, maybe you have to draw this out for yourself. Let's say that's normal, and let's say that's shifted. What I had said was, normally, at 27, that gives you your standard 50% saturation. But if you shift it, it's like, you gotta go some higher number to get 50% saturation. So another way to put it is, the Bohr effect, you're facilitating more loading. It takes more O2 to achieve 50% saturation, okay? That's kind of when I said the chair is not flat but slanted down, right? That's what I said for that. So let's not even put a number to it. Let's just say Bohr effect, does that increase or decrease P50? Increases it. You guys see that? Well, kind of on the same thing, you could shift the curve the other way. Does P50 increase or decrease with the left shift? Decrease. Shift left, P50 decreases. Okay, so that's very standard thing. No P50, the number is 27. Under normal conditions. Okay. All right, so let's say you're exercising, you're huffing and puffing, and you're actually doing the Bohr effect, where you're actually going to unload more. That's why I put Bohr here. If you unload more, you can load more CO2. You see that? They go hand in hand. If more oxygen get off the bus, more CO2 can get on the bus, so to speak, using my analogy though. That's called the Haldane effect. Haldane. So, okay, I'm going to erase P50 here. So first thing, Bohr effect. Thinking is, facilitates more O2 unloading. There's a consequence of that. This more O2 unloading allows a couple of things. Number one, more CO2 loading, particularly to the hemoglobin, the carbaminohemoglobin. HbCO2 is that carbaminohemoglobin. And also, secondly, you shift this equation to the right. You shift carbonic acid equation to the right. So you're getting more bicarbonate into the bloodstream. So with number 1 and number 2, what you're doing is you're getting more CO2 into the blood. Increase arterial CO2 content. Of course, the name for that is Haldane effect. So CO2 loading, more of it is Haldane, but it's only the result of more O2 unloading, which is the Bohr effect. Okay, so they kind of go hand in hand. But first Bohr, then Haldane. So that second point there, I want to show you on the slide. That second point, where you shift the carbonic acid equation to the right, is shown on the figure. I'll turn the lights off so you can see that better. What they show you here, that fast reaction with carbonic anhydrase. In order to get it off the surface, you have to perform what's called the chloride shift to get it in the plasma compartment off the surface. So you exchange a negative charge for a negative charge. You just kind of exchange the bicarb with the chloride. We call that the chloride shift. So now you're in the bloodstream, and you're going to take that CO2 to be exhaled at the lungs for external respiration. So what you got to do is just everything in reverse. You take that carbamidal hemoglobin and you release the CO2 to cross the respiratory membrane, and also you take that equation and you shift it to the left. So you have to do the reverse of the chloride shift to get it on the surface of the red blood cell. And then you just have to get the bicarb in the CO2 form so you can breathe that off, okay?
Where did the chloride come from?
Oh, we have chloride in your plasma compartment. Yeah, it's just there already. All I want you to understand with this is the concept. Look at the lighter blue curve. This is like, it's saying HB saturation is 0. I mean, it's never 0, right? The point is, when it's less saturated, you get more CO2 in the blood. That's the only point I was trying to make with the Haldane. Okay. So to start to sum up here, let's kind of go through this as a class, so people who are just kind of, I'm starting to get this. Maybe you can catch up a little more. Let's do this. I want to survey the class. Give me a, don't do it yet, but I want you to give me a thumbs up. I just finished most of the lecture. Okay, yeah, I'm getting this. Boom, got it. Give me a thumb sideways as, I don't got it yet, but I will. This is not that hard. And give me a thumbs down. And I have no idea what you just talked about. Okay, right now, everyone, thumbs up, thumbs sideways, thumbs down. Okay, some people are lost and some people aren't. So let's try to bring it all together now. Let's pretend you're exercising and consider these 4 things. Is it more or less acidic? It is more acidic, okay? Let's address that in terms of pH. If it's more acidic, is pH increased or decreased? Decreased. Okay, that's thing number 1. Okay. When you're working out, when you're exercising, is the partial pressure of CO2 in your blood higher or lower? It's higher, it accumulates, and that's today's lab. Today's lab, you're gonna blow into a solution that's basic. And the CO2 in your exhaled air will make it turn clear because you're going to turn a basic solution more acidic. And the way you're going to tell is there's a pH indicator that turns it pink. And when you blow it, make it acidic, it goes from pink to clear. And that should happen no matter what. But if you're exercising, after working out for a few minutes, you should have more CO2 in your exhaled air, and it should turn from pink to clear more quickly. So you have to type. That's today's lab activity. Continuing on. When you're exercising, a partial pressure of PCO2 increases. What about BPG? It's higher. Right. And your body temp when you work out? It increases. So these are the factors besides PO2 I was talking about. All right, so these factors. Now I was talking about the Bohr effect and you shift the curve and stuff. Which way did you shift the curve? To the right or to the left? Right. To the right. That's this figure, correct? The solid line is normal. The dotted line is like a rightward shift. Shift curve to the right. Okay, so A through D, these four things here, does it facilitate, circle one that's correct, does it facilitate oxygen loading or oxygen unloading? Oxygen unloading, that's correct. You get more unloading. Did we call that Bohr or Haldane? Bohr. We did call it Bohr. So which choice is correct? D is a dog. More unloading, and we called that the Bohr effect. That was the rightward shift. So this is Bohr. Then what I said was, as a result of more O2 unloading, we get more CO2 loading, or particularly onto the carbon, on the HB, and that's the Haldane effect. So as a result of Bohr, you get Haldane. I put this in just to make sure that these are common questions I want to make sure you've answered. And the ones on the right, I did them all. Okay. Oh, I did 5 and 6. Ooh, I didn't do 7. I better do this one with you. Before I do this with you, let's make sure we can answer these questions here. I'll give you the answers. Just write down the answer. You can quiz yourself later, but let's try to do it together as a class. I say, what's the number one way oxygen is transported in the blood? And the answer I'm going for is C. If you can't read that in the back, it says in the form of oxyhemoglobin. That was like 90, almost 98%, right? Even more. What is the number one influence on hemoglobin saturation? Of these choices, the biggest one was D, the PO2. That was the number one thing. It gave us that sigmoid-shaped curve. Okay, what is hemoglobin saturation at altitude in the mountains? Of these three numbers, if you can read them. B is correct. That says 83.5%. The point of that was, even when you're breathing air that's a lot thinner, your hemoglobin is still pretty good at getting saturated. The plateau part of the oxygen hemoglobin saturation curve ensures that hemoglobin will be mostly saturated, regardless if one lives at altitude or sea level. Is that true or false statement? That is all true. Okay. So, if we're not quite following that, write the answers down, study some more, and recheck for your understanding. For now, for all of you, for calculations on the test, I may have you do this. So let's go through it. Here's what I got to give you. calculate the O2 content, total arterial O2 content. I got to give you the amount dissolved in the blood. Here it's 0.3. We have to remember that per gram of hemoglobin, it can bind 1.34 mil of O2. Per gram of hemoglobin. I would also have to give you a person's hemoglobin concentration in the blood. I mean, I gave you a normal range. It's like 12 to 18. Here it's like 15. 15 grams HB per deciliter of blood. Well, the first thing I do is I try to figure out how much oxygen is bound to hemoglobin. So I'm going to take this bottom figure, 15 grams hemoglobin per deciliter of blood. What I know is, in humans, it binds about that much. So I'll just multiply by that factor. I'm going to cross out the units there, and I'm left with 1.34 times 15. Yeah, multiply that. I get 20.1 mil O2 per deciliter of blood. However, this is the amount of oxygen bound to hemoglobin. I'm not done yet. What's the other way you transport O2? This one. So I just have to add it. I'll just add this to this. This is the amount bound to hemoglobin. The amount dissolved, I'm just going to add it. 0.3 mil O2 per deciliter blood addition. Add it together, 20.4 mil O2 per deciliter blood. That is the answer, 20.4. So that's how you do it. I mean, obviously I would change the numbers a bit for an exam, but functionally, figure out how much bound hemoglobin and then just add the amount that's dissolved. Okay? Any questions on the calculation? Let me explain your lab. We'll shift gears in the lab. It's not a long lab, so it's not much time. You got 50 minutes. Shouldn't take you that long. You can work in groups and just turn in one per group if you want. It's really simple. I'm going to walk over here. It says, fill a beaker with 200 ml of artificial blood. This is artificial plasma. It's a little bit basic, and we got beakers here. Okay. You need 200 ml because you got to do a pre-post. So you need 100 for pre-exercise and another 100 for post-exercise. So take 200 is a beaker. But also, take one of these. Okay. Now what you got to do, when you get your 200 ml of fake blood, you have to add your indicator. So they say add about 20 drops. This is our indicator. Obviously, it'll make it pink, right? Something like 20 drops. So what you want to do is you got your 200 ml of your pink. Take half of it, 100, and put it in your flask there. Okay. This is before you exercise. So we give you some parafill.
in your breath. So when you come back, dump the first 100 mil. Dump it over there in the hood. See there? Big funnel. Dump it all the waste in there. Put your other 100 ml and then parafilm it and then blow again at the same rate, just nice and easy, and it should clear up quicker. That's the extra neat. Go ahead and get started.